Hello, everyone. Thank you for coming for the third episode of the second season of the Young Researchers Forum on Detonation. And today our speaker is Ms. Yaroslava Poroshyna. She's currently a PhD student in applied mathematics at the Moscow Institute of Physics and Technology. And also a junior research assistant at the Institute for the Computer-Aided Design of the Russian Academy of Sciences. At MIPT, Ms. Poroshyna received her bachelor and master degrees in applied mathematics and physics, supervised by Professor Utkin. Ms. Poroshyna's current research mainly focuses on the understanding of nonlinear dynamics of detonation waves, propagation in gaseous mixtures using simplified chemical kinetic model via numerical simulation and analysis. Now I will give the time to Ms. Poroshyna. Please go ahead and start your presentation.
Okay, thank you. Yeah. Thank you for the introduction. The topic of my talk today is the dynamics of detonation wave propagation analyzed in the shock-attached frame. To start with, I would like to say that detonation is a hydrodynamic wave process of the supersonic propagation of an exothermic reaction through a substance. The detonation wave is a self-sustained shock wave discontinuity, and behind its front, a chemical reaction is continuously initiated due to heating caused by adiabatic compression. Here is the pressure profile of an ideal one-dimensional detonation. It consists of the von Neumann peak, followed by the reaction zone. In the end of the reaction zone, the parameters are equal to theoretical parameters, Chapman-Jouguet parameters. Depending on the kinetics model of chemical reactions, the reaction zone may be of finite or infinite length. The picture on the right represents the typical parameter profiles in the steady-state solution called ZND solution. Theoretical and numerical studies of the stability of Zeldovich-von Neumann-Döring solution describing a stationary detonation wave as well as pulsating modes of detonation wave propagation go back to the works of Erpenbeck and Fickett. A large number of subsequent fundamental studies of pulsating detonation wave are associated with the use of a single-stage model of kinetics of chemical reactions. On one hand, this is due to the considerable degree of development of this model, the well-established methodology of transition to dimensionless variables using the length of the half reaction, and a large amount of accumulated data. On the other hand, it is known that this model is able to describe the main features of nonlinear dynamics of detonation wave propagation, such as one-dimensional pulsations, two-dimensional detonation cells, and three-dimensional spin. This slide represents the pressure profiles obtained for one-stage and two-stage kinetics model of chemical reactions. In one-stage kinetics model, all heat release occurs in the whole reaction zone after von Neumann peak. However, among the disadvantages of the model, there is the impossibility of explicit separation of the induction and reaction zones. It was a background for creation of two-stage models of kinetics. Picture on the left represents profiles of pressure for different values of activation energy for one-stage kinetics model. Larger activation energy, it's the dotted line, permits to distinguish the induction zone, where the parameters are almost constant, even though it is not described explicitly by the model. It becomes impossible for a smaller value of activation energy, solid line. And the picture on the right represents also pressure profiles, but for this two-stage model. It can be observed that the length of the reaction zone is finite, and mixtures with different ratios of induction and reaction zone length are described equally well. Korobeynikov and Levin were pioneers in the development of a two-stage kinetics model of chemical reactions. Then Markov and Levin were the first to perform a theoretical study of two-dimensional detonation using a numerical method and a two-stage model. In this paper, they considered the initial stage of the development of a two-dimensional flow in a plane channel as a result of the passage of a plane detonation wave initiated by a point explosion through a combustible mixture in which there is a weak local non-uniformity of density. The formation of a peculiar fracture of the detonation wave front was found. It proved that weak non-uniformity of reactant mixture might be one of the reasons behind the occurrence of non-one-dimensional flow. These ideas were used by Fujiwara and Doran with co-authors in order to study the origin of two-dimensional cellular structure. Okay, so Korobeynikov, Levin, Markov, and Chorny were the first to introduce the two-stage kinetics model of chemical reactions for detonation. Theoretical study of properties of one-dimensional pulsating detonation wave using two-stage kinetics model was performed in the work of Short and Sharp. Here, the asymptotic stability analysis was made. The next work was the continuation of this study. The bifurcation diagram was built and the stability parameter was introduced. So on the picture on the left, the reaction constant is along the horizontal axis, while the local maximum oscillation amplitude is along the vertical axis. It can be seen that if the reaction constant is less than the critical value denoted as the neutral stability boundary, the detonation is stable. When the reaction constant increases, the oscillations appear and their amplitude also increases until the next critical value of the rate constant is obtained. After that, the oscillations of several amplitudes are present in the solution. And the subsequent increase in the rate constant leads to the appearance of oscillations of different amplitudes and results in the chaotic propagation of the detonation wave. In addition, this paper, as the following papers, used detailed kinetics mechanism in order to obtain parameters for two-stage kinetics model, and thus we're able to study real mixtures, but using more simple model of kinetics. We now turn to the description of the statement of the problem, and I'd like to simulate the detonation wave propagation in the shock-attached frame. The advantages of simulation in the shock-attached frame are the following. So at first, the leading shock wave and parameters behind it are explicitly tracked, and it makes the analysis of pulsating detonation wave propagation more simple. And the second, it's that the simulation time is considerably reduced as we don't have to initiate the detonation from the beginning. So we perform one-dimensional simulation. The computational domain is a segment of the length L. That in this solution was used as initial conditions. Rankine-Hugoniot relations were used as boundary conditions on the right boundary due to the fact that we considered a problem in the reference frame attached to the shock. And Chapman-Jouguet parameters or extrapolation were used as rear boundary conditions. The governance system is presented on the slide by one-dimensional Euler equations and two-stage chemical kinetics model. This system should be supplemented by an additional equation that defines variable d, which is the detonation velocity. It should be noted that we have transferred to the non-inertial coordinate system, and thus the shock velocity evolution equation has to be solved each time step. There are several major approaches devoted to simulation of detonation wave in the shock-attached frame. The first is based on the paper of Kasimov and Stewart. Here, first approximation order scheme was used, and shock speed was calculated by integration of the governing equations along the C+ characteristic near the shock. A test with a shock overtaking another shock that was used in this paper demonstrates the stability of the algorithm to detonation waves numerical calculations. As a result, main regimes of detonation wave propagation were obtained. The shock dynamics is shown to be determined entirely by the finite region between the shock and the sonic locus. And the second approach adopted the fifth approximation order Wiener scheme and fifth order Runge-Kutta scheme. The shock speed evolution equation was obtained while connecting with the momentum flux gradient, and this approach has a restriction: it may describe only strongly unstable detonation waves. We have chosen the Kasimov approach as it seems to be most stable while calculating strongly unstable regimes. Lately, the authors of the second approach have improved it, and it is able to deal with strongly unstable regimes too, but not with the fifth order. So we used the dimensionless parameters, and here one can see the procedure of transition to these parameters. Von Neumann parameters were used as characteristic scales for pressure and density. And this is the expression for the Mach number using non-dimensional parameters. And parameters in front of the detonation wave are calculated using Rankin-Hugoni relations. The characteristic scale for the x-coordinate is the induction zone length. The computational algorithm is based on the physical processes splitting technique. The system is discretized using finite volume method. Second order was achieved using min-mod limiter. The numerical fluxes were calculated using a variant of grid characteristic method, current Isaacson-Rees scheme. Time integration was performed using explicit Euler scheme. Algorithm of integration of the leading shock wave velocity demands some explanations. The governance system is written in the characteristic form, and it is integrated along the C+ characteristic. The picture on the right represents where the C+ characteristic is in relation to the cells. X sub star is the coordinate of intersection of this characteristic with x-axis. Parameters in this point are calculated using linear interpolation and data in the center of the last computational cell and exactly on the boundary. So exactly on the shock. This is the discretized form of the first equation, and this coordinate might be found analytically using linear interpolation to determine parameters in this point, and then these parameters are substituted in the first equation. After that, the second equation with the unknown variable, which is the Mach number, is solved using the Newton method. And once the Mach number is determined, the detonation velocity is also found. The computational algorithm was tested using the test of the shock overtaking another shock, which was originally taken from the book of Roshtestynsky and Yanenko. So two shocks are moving from the left to the right, and one is moving at a velocity which is greater than the leading shock. At the time moment approximately 1.11, the faster shock reaches the slower shock. They coalesce and move in the same direction. It may be seen that the leading shock velocity reaches the exact solution. The considered problem qualitatively describes the situation that arises frequently when a detonation wave propagates. The secondary shock wave catches up with the leading shock wave, and it strengthens and accelerates the leading shock. In addition, it can be seen that as a result of interaction of a shock wave with another shock, a rarefaction wave and a contact surface are formed. I will start with the consideration of the high-frequency regime of detonation wave propagation. These figures demonstrate pressure and density profiles shifted by 0.1 from each other for clarity. At first, the contact surface moves to the left across the induction zone towards the reaction zone. At the moment when the contact surface reaches the beginning of the reaction zone, the strong compression wave is generated, which moves to the right until it catches up with the leading shock. It strengthens the leading shock front, creates a new contact surface, and then a new cycle begins. Similar to the paper of Leon Rodolesco and Sharp, we at first studied 4 regimes of detonation propagation, namely the high frequency, very high frequency, low frequency, and transition regimes. They are named so according to the period of oscillations occurring at the detonation wave front. So in the high frequency regime, the period of pulsations is greater than the induction time, but is comparable to it. In the very high frequency regime, the period of oscillations is less than induction time. In low frequency regime, the pulsations period is much greater than the induction time. And the transition regime is interesting as it combines high frequency and low frequency pulsations simultaneously. Here, the front pressure history is presented on the figures. The red lines here and on further pictures represent the second order calculations, where zero order extrapolation was used as far field boundary conditions. Green lines denote the calculations where the CJ parameters were used for this purpose. Black lines denote the digitized data from the Leung study. It should be noted that the study taken for comparison was performed in the laboratory coordinate system, and in their paper, the detonation propagated across the fixed domain, whereas the non-reacted material ahead of the detonation wave was stationary. It can be seen that extrapolation and Chapman-Juget parameters taken as the boundary conditions do not affect the solution. Moreover, the period and amplitude of pulsations coincide with the data from the study of Leung, Radulescu, and Sharp. In the transition regime, the solution obtained in the laboratory frame also coincides with our solution. And to the best of our knowledge, this regime has not obtained much attention in literature, and we will focus in more detail on it here. There have been attempts to capture this complicated nature of the regime with the one-stage kinetics model. However, they have been unsuccessful. Similar mode of detonation propagation was obtained using the detailed kinetics in a different study. So it seems that despite being quite simple, the two-stage kinetics model is able to capture the complicated dynamics of pulsations of mixtures, of real mixtures. Next, I'd like to show the video of propagation of the spatial profiles of pressure, density, and direction and induction zones progress variables. We will start at approximately 2015, which is the time variable is equal to, approaching the point of detonation velocity and pressure global minimum. Here one can see that interaction of a compression wave with leading shock creates the contact surface traveling across the induction zone to the left. Actually, the rarefaction waves are also formed, but are almost indistinguishable at first. I would like to know that at some point, the pressure drop on the rarefaction waves becomes greater, and we can see that interaction of the rarefaction waves with the reaction zone also creates a compression wave. And here we saw that at the same time, two compression waves were traveling across the induction zone, creating their own contact surfaces and catching up with each other. Once these compression waves catch up each other, they coalesce and the resulting shock weakens. The length of the induction zone, as it can be seen, it increases until the cycle starts from the beginning. You can see now that the parameters drop on the compression waves and contact surfaces become greater again. Now we shall proceed to pictures. We shall describe both periods of pulsations, high frequency and low frequency, that arise in the transition regime, starting with the end of the deceleration part of the cycle. This part is defined by a decrease in the leading shock velocity and corresponding decrease in front pressure, and by gradual increase in the induction zone length. On this picture, we observe the compression wave moving to the right across the induction zone. When this compression wave, the first compression wave, reaches the end of the leading shock, it amplifies the shock, although the overall front pressure as well as the front velocity still decrease. After that, the rarefaction wave and the contact surface start moving across the induction zone to the reaction zone. The rarefaction wave moves faster than the contact surface. It might be seen from the slopes on this slide, which represents the characteristics for this part of the cycle. So arrival of the rarefaction wave and the contact the rarefaction wave. Arrival of the rarefaction wave to the reaction zone leads to the occurrence of another compression wave, while the contact surface still moves across the induction zone. When the contact surface arrives to the reaction zone, the new compression wave is generated, and the pressure drop is now greater than on the compression wave number 1, and is even greater than on the compression wave number 2. It means that the contact surface and the rarefaction wave generated after this interaction with the leading shock wave are also of greater amplitude. However, this time the rarefaction waves no longer influence the appearance of the compression waves. Moreover, the induction zone length starts diminishing gradually, and the reaction zone comes closer to the leading shock. So as I said earlier, it can be seen from the C plus and C0 characteristic slopes that the velocity of propagation of compression waves and contact surfaces remain the same. Here, black lines denote C plus characteristics. Blue dotted lines are the particle paths, C0 characteristics, and red lines denote C minus characteristics. So as the induction zone narrows, the distance between the waves decreases too. And here on this picture, it can be seen better. And on the spatial profiles, it can be seen that the contact surfaces are now moving in the same direction, catching up each other at the arrivals to the beginning or ending of the induction zone. On the third picture, the contact surfaces are almost indistinguishable from each other. And here they coalesce into one compression wave after interaction with the end of the reaction zone or of the induction zone. This fact signalizes the end of the acceleration part of the low frequency cycle. So we are here now. After that, the amplitude of the waves moving across the induction zone diminishes and the velocity of the leading shock front decreases. At approximately 2166, it's somewhere here, the pressure peak of the smallest amplitude is observed. I mean, these small peaks. And it corresponds to the value slightly above the steady detonation value, which is unity. Further, the front pressure continues decreasing globally. However, the high frequency local pressure peaks are now of greater amplitude. Eventually, the pressure drop on the rarefaction waves generated after interaction of compression waves with the leading shock wave starts increasing, and the compression waves are now produced not only due to interaction of the contact surfaces with the end of the induction zone, but also due to arrival of the rarefaction waves to this point. And then the cycle starts from the beginning. So now the first part of my talk ends, and I would like now to talk about the simulation of propagation of a shock wave in the non-uniform medium, and a little introduction to this part. So nowadays, people are trying to use detonation to develop new types of engines. Over the last several years, Foundation for Advanced Research conducted 2 projects devoted to the creation of different detonation engines. One type of detonation engines is the rotating detonation engine. The basic concept of such engine is a detonation wave that travels around a circular channel. Fuel and oxidizer are injected into the channel, normally through small holes. A detonation is initiated in the fuel oxidizer mixture by some sort of igniter. After the engine is started, the detonations are self-sustaining. One detonation ignites the fuel oxidizer mixture, which releases the energy necessary to sustain the detonation. The combustion products expand out the channel and are pushed out of the channel by the incoming fuel and oxidizer. What is important for the current study is that the separate injection of fuel and oxidizer creates the inhomogeneous mixture ahead of the detonation wave. Therefore, it is crucial to understand the dynamics of such detonation wave propagation. And the first step is to consider the one-dimensional detonation wave shock wave interaction with the mixture with variable density ahead of it. For this reason, we will consider a Shu-Osher test problem, which is well known in literature. Picture on the left represents the statement of the problem in the laboratory frame. The shock wave of Mach number, which is equal to 3, interacts with the medium with the sinusoidal perturbation of density. The picture on the right represents the pressure profiles at the time moment approximately 1.8. According to Suresh and Rawat, as the shock wave moves through the medium with varying density, an oscillating solution is formed behind its front. At any moment in time, this oscillating solution is limited by a rarefaction wave on the left, a contact discontinuity in the middle, and a traveling shock wave on the right. Over time, this oscillating solution becomes steeper and forms a shock train behind the wavefront. But for earlier moments in time, the solution behind the wavefront remains continuous. This problem has been traditionally used as a test case for shock capturing schemes because it contains both a smooth structure and a moving discontinuity. However, these researchers claim that they state that the mild version of the Shu-Osha problem is a better test case. In the original formulation of the problem, the first derivative of density was not equal to 0 for x greater than this point. Whereas in the case in this case, the first, second, and third derivatives are equal to 0. This change provides a soft onset of interaction and smoothes the rarefaction wave and contact discontinuity behind the shock wave. But at the same time, such initial density distribution retains the main features of the solution, namely high frequency oscillations behind the traveling shock wave. The figure below shows the solution at a time when it is still continuous behind the shock wave. However, we will still consider the original Shu-Osha problem. And we also consider this problem in the shock-attached frame. The computational domain is a segment of the length L. The leading shock is considered stationary in this formulation. The density distribution ahead of the shock wave is non-uniform, and in fact, it is dependent on the shock front velocity, which is different each time step because of the non-inertial coordinate system. It leads to the following system of equations to solve. Apart from the governance system being written in the characteristic form as before, an additional relation for density ahead of the shock wave is considered. There are different ways to discretize the system. The first one that we considered, we call the explicit one. It follows the study of Kasimov and Stewart that I talked about earlier. Here, the first and last equations depend on the parameters from the current time step, here and here. The semi-implicit algorithm eliminates parameters from the current time step in the first equation, but still leaves these parameters in this equation. And the implicit discretization scheme leads to a fully implicit algorithm and the need to solve the nonlinear system of 3 equations using Newton method. It turned out that the first and second schemes were unstable, and when the shock train started to form, both algorithms failed to find the solution of the corresponding nonlinear systems. So we used the implicit version. As this algorithm turned out to be more stable, provided also that the initial guess for the Newton method was modified. So the solution from the previous time step was considered unless the algorithm failed to find the solution in 20 iterations. Then the solution from the previous local minimum was used as the initial guess. The red line on the picture represents the point of intersection of the C+ characteristic with the right boundaries that corresponds to the leading shock. The green line denotes the calculated values of density ahead of the shock wave that were encountered by the shock wave. And the blue line denotes the calculated corresponding Mach number of the shock wave. These are the parameters that were found iteratively in the simulation. And this slide represents the velocity of the leading shock. It can be seen that the maximum velocity of the leading shock is approximately the same, while the minimum velocity gradually increases. So the shock accelerates while moving through a perturbed medium. It should be noted that flow upstream of the shock is supersonic relative to it, hence no effects of interaction will propagate upstream in the shock reference frame. It can be seen from the figure that the density disturbance amplifies after passing through the shock and causes nonlinear waves downstream. As the shock propagates into the varying density field, an oscillatory solution develops behind the shock. A contact discontinuity develops in the middle of the flow downstream of the shock, separating the region immediately behind the shock from the small shocklets further downstream. We compared our solution with the one obtained in the laboratory frame, and and the one presented in the original paper of Xu and Doscher. We also used the results obtained in a different shock tracking algorithm proposed by Rawat with co-authors. It can be noted that in our algorithm, the slope of the density curve slightly varies from the data taken for comparison, and some further research should be carried out in order to gain deeper knowledge of the nature of such differences. So overall, the computational algorithm was proposed for the simulation of detonation wave propagation using two-stage kinetics model of chemical reactions, and it was simulated in the shock-attached frame. We applied this algorithm to simulate the main regimes of detonation wave propagation that are high frequency, very high frequency, low frequency, and transition regimes. And we tried to explain the dynamics of the transition regime in the characteristics analysis. Also, we modified the algorithm for the simulation of a shock wave interaction with a non-uniform medium and compared our results with the data from other studies. That's all. Thank you for your attention. Thank you.
Yeah. Okay, thank you. Thank you for your presentation. Yeah. Is there any questions from the audience? You can either type your question in chat or just I will read for you, or you can unmute yourself and ask directly. There is a comment and a question from Professor Andrew Higgins. I will just read his question. He said, this is very interesting work. The use of a shock-attached frame greatly assists in interpreting the wave interactions in unsteady detonations, as was well shown by your animations. In connection with the use of a shock-attached frame, in the slide showing governing equations, I was concerned that I did not see a pseudo-force term that should be present when using a non-inertial frame. In particular, there should be a term rho dt, derivative of detonation velocity with respect to time in momentum equation, and a rho u dt term in energy equation. Why are these terms not present?
No, they're present, so it can be seen here. I just didn't write them explicitly. Do you see my screen now?
Yeah, I'm seeing.
Sorry,
yeah.
I am a co-author and I can answer the question. The point is that u here is the velocity in the laboratory frame. Although we consider the system in the shock-attached frame, u is velocity in the laboratory frame. And if we introduce velocity in the shock-attached frame, it will differ in the term d, and so we will see the dd, the term that Professor Higgins mentioned. So it's just because u is the velocity in the laboratory frame.
Okay. Yeah, interesting. Is there any other questions? I have a question, or I just I wonder, like, what would be the next step using this to simulate an inhomogeneous medium? Like, what would be the problem setup?
Well, at first, it would be interesting for our understanding, maybe, to simulate this test.
Mm-hmm.
So the more mild version, and to see how this different versions of algorithm manage to do that. And after that is to simulate detonation wave propagation with also the non-uniform medium in the shock-attached frame.
Okay. And for the inhomogeneities, like the shock wave is going into, does it have to be continuous? Like if you have like very sharp or like sharp discontinuities in the inhomogeneous distribution, will your algorithm still work?
I think yes, but you see that the algorithm has to be modified each time when the medium before the shock wave or the detonation wave. Sorry. So the algorithm has to be modified every time. If we change the law for the density, for example, then the algorithm has to be modified. If we take, as you say, some sharp inhomogeneities, then the idea will remain the same, but it still has to be modified, and we didn't do this. I think it will manage, but we have to check.
Okay, I see. Yes, very interesting. Yeah, I'm looking forward to see this more like this inhomogeneous case result. I think this will be very interesting.
I understand. Yeah. Thank you.
Yeah, thank you. Is there any other questions from the audience? Let me see the chat. If there's not, then I would like to thank Yaroslava for her talk again. I think this is very important for us to, before you actually use a simulation, actually do this thorough tests. I believe these days, like there are many researchers in Detonation, they actually use like a group code or a code that people have been developing over years, but the students who are using it are not really making sure that they understand the backend algorithm, or they just don't do a very thorough tests of the code. I believe this is very important. This should be the first step we do before getting any research results. And this is a very good example of that. Yeah. Thank you for your time for preparing this, and we're looking forward to more future results from you.
Thank you for your comments.
Yeah, thank you. And next week we will have Professor Pavel Woodkin, who's the supervisor of Yaroslava, presenting. Right, they will be in 1 week at the same time next week, next Monday. Okay. Yeah. Thank you all for your attendance today, and we will edit the video and send to Yaroslava for her approval, and after that we'll upload that to our YouTube channel. Right? Is there any other announcement you want to make, Shen?
I just want to thank Yaroslava again for her presentation, and I look forward to results. As Yao Cheng said, it's nice to see something that you've kind of described the way you're going about developing your code, and it'll give a lot more confidence to your results. So that's good.
Thank you.
Yeah, thank you. Thank you for your time, and have a good day and have a good night. Hope to see you all next week.
Thank you.
Thank you. Bye-bye.
Bye.